Welcome to this lecture on Continuous Extension Theorem by Dr. Rajesh Singh.
Welcome back everyone. So today we are going to learn about very important theorem which is continuous extension theorem. So using this theorem you will be able to tell almost everything about a continuous function and when it can be uniformly continuous. So this theorem along with the uniform continuity theorem where we have proved that every continuous function defined on a closed and bounded interval is uniformly continuous. So this continuous extension theorem along with uniform continuity theorem will tell you a lot about uniform continuity. So basically we have already seen that every function defined on a closed and bounded interval is uniformly continuous. Also we have seen the function fx equal to 1 by x which is continuous on the open interval 0 to 1 but not uniformly continuous on that interval. So what can we say about the uniform continuity of a function when it is defined on a bounded open interval? So this is what we are going to conclude using this continuous extension theorem. So basically we are going to show that a function is continuous on an open interval AB if is uniformly continuous on an open interval AB if and only if we can extend that function to a continuous function on the closed interval AB. So this is what we are going to do in this continuous extension theorem. So before going to continuous extension theorem, we are going to prove another very important theorem, which is that uniform continuous image of a Cauchy sequence is a Cauchy sequence. So basically, if if we have a uniformly continuous function f and if we have a Cauchy sequence xn, then its corresponding sequence fxn is also a Cauchy sequence. So that is what we are going to prove first. So let us just see the statement of this theorem. So here we are given a uniformly continuous function f defined on a subset A of R, and if xn is a Cauchy sequence in A, then we will show that fxn is also a Cauchy sequence in A. So let us start its proof. So given f is uniformly continuous on A, and second xn is a Cauchy sequence in A. To show f of xn is a Cauchy sequence in R. So we are going to prove that f of xn is a Cauchy sequence in R, and what we mean by a Cauchy sequence? A sequence xn is a Cauchy sequence if for each epsilon greater than 0 we are able to find some positive integer p such that xn minus xm is less than epsilon whenever nm is greater than equal to p. So that is what we are going to prove. So we will start with any arbitrary epsilon and we will try to find a positive integer p. Let epsilon greater than 0 be any real number. So now we will use the continuity of f. So since f is uniformly continuous on A, so for above epsilon greater than 0 there exists delta greater than 0 such that our fx minus fy will be less than epsilon whenever x minus y is less than delta and xy belongs to A. So mark this as star. Now we will use the fact that xn is a Cauchy sequence. We will use this delta for it. So since xn is a Cauchy sequence, so for above delta greater than 0 there exists p belonging to z positive. So we are using the definition of Cauchy sequence. So there exists p belonging to z positive. So instead of epsilon we are choosing this delta because we want our xn to satisfy this condition xn minus yn. We want this condition to be satisfied by points of xn. So that's why we are going to take delta in place of epsilon. So there exists p belonging to z positive such that xn minus xn is less than delta, because we are taking delta in place of epsilon, less than delta whenever nm is greater than equal to p. So now we have that xn minus xm is less than delta, uh, and when xn minus xm is less than delta, so fxn minus f by x fxm will be less than epsilon. So using star in double star, we conclude that fxn minus, so we instead of in place of x we are using xn because xn and xm are satisfying this condition. So in place of x we are using xn, and in place of y we are using xm. So fxn minus fxm is less than epsilon for all nm greater than equal to p, because whenever nm is greater than equal to p, then xn minus xm is less than delta, and because xn xm is a Cauchy sequence in A, so this belongs to A, so it satisfies this property. So fxn minus fxm will be less than epsilon. So this implies f of xn is a Cauchy sequence in R, hence proved. So this completes the proof of this theorem. So basically it means that the uh, uniform continuous image of a Cauchy sequence is a Cauchy sequence. So in simple words, so hence we have shown that the image of a Cauchy sequence under a uniformly continuous function is a Cauchy sequence. So this result is very important because we use this result at lot of places in lot of theorems. So in fact the theorem that we are going to do next, continuous extension theorem, so we are going to again use this theorem there. So you, to remember this result we must remember this fact that image of a Cauchy sequence under a uniformly continuous function is a Cauchy sequence. So now let us see examples. So we will take two examples. So example 1, fx equal to x square on 0 to 1. So fx equal to x square, this is uniformly continuous. So a equal to 0 to 1. So then xn equal to 1 by n for all n belonging to n. So xn is a Cauchy sequence in 0 to 1. Also f of xn, which is equal to 1 by n square, is also a Cauchy sequence because this function is uniformly continuous on the closed interval, on the interval 0 to 1. Cauchy sequence in R. Now let us take another example. So we take a function fx equal to 1 by x on interval 0 to 1. So we know that fx equal to 1 by x is not uniformly continuous on the interval 0 to 1. So we know that f is not uniformly continuous on 0 to 1. So we have taken this function fx equal to 1 by x, it is not uniformly continuous. Now if we take the sequence xn equal to 1 by n, then xn is a Cauchy sequence. So xn is a Cauchy sequence in 0 to 1, but f of xn is not, f of xn which is equal to n is not a Cauchy sequence, in fact it is an unbounded sequence. Note that every Cauchy sequence in R must be convergent. We know this result that a Cauchy sequence is a sequence is convergent in R if and only if it is a Cauchy sequence. And it is also interesting to note that if this set was closed, now 1 by so this function f is not uniformly continuous on the interval 0 1, so we are getting that the corresponding sequence need not be a Cauchy sequence. So this result can be used in negating something. So in negating a uniformly continuous function, so if we have some if we take a Cauchy sequence, so this can be so from here we can also conclude that f is not uniformly continuous, because xn is a Cauchy sequence in 0 1, but fxn is not a Cauchy sequence. So from this theorem we can easily conclude that f is not uniformly continuous on 0 1. So this is also one of the proof to show that f of x equal to 1 by x is not uniformly continuous on 0 1. In fact, so one we can conclude this result from this. Okay. So now let us move to the continuous extension theorem. So what this theorem says that a function is uniformly continuous on an open interval if we can extend that function to a continuous function on the closed interval AB. So this is very important theorem. So if you have some, so if you look at this function fx equal to 1 by x on 0 to 1, so you cannot define this continuously on the closed interval 0 to 1, right? Because limit x tends to 0 positive f of x does not exist. So we cannot define f continuously on this. So we cannot define f such that it is continuous on the closed interval 0 1. We cannot define we cannot extend this function f to a continuous function. So this theorem says that a function f is uniformly continuous on the interval ab if and only if it can be defined at the endpoints a and b such that the extended function is continuous on ab. Extended function continuous on ab means that limit extends to a positive should exist and limit extends to b negative should exist. So in other words, this theorem says that f is uniformly continuous on AB if and only if f is continuous on closed open interval AB first, second limit x tends to a positive fx exist, and third limit x tends to b negative fx exists. So if these three things are satisfied, then f is uniformly continuous on the open interval AB. So basically it means that f is uniformly continuous on open interval AB if and only if f is continuous on the open interval AB, limit at the point so RHL at the point A should exist and LHL at the point B should exist. So if these three conditions are satisfied, then we say that f is uniformly continuous on open interval AB. So you can easily now, given any function, you can easily say, because now you can easily say that fx equal to 1 by x is not uniformly continuous on 0 to 1, because you can limit x tends to 0 positive fx does not exist. So you can easily conclude from this theorem. So now let us, while your function fx equal to x square is uniformly continuous on any open interval AB, because limit x tends to a positive fx is equal to a square and which exists, and limit x tends to b negative fx is equal to b square, and clearly f is continuous on the open interval AB. So this is uniformly continuous. So using continuous extension theorem, you can easily say which function is uniformly continuous and which function is not. So you just need to have this property. Let us now write its proof. So so first we assume that f is uniformly continuous on the interval AB. So assume that f is uniformly continuous on open interval AB to show f can be extended to a continuous function on closed interval AB. So basically we have to show that these two limits exist. So for that, what we will do, so that is to show limit x tends to a positive fx exists and limit x tends to b negative fx exists. So for this we will take we will show that this limit exists and equals some real number l. So that we will show, and this can be followed on the similar lines. So we will just prove the existence of this, and this can be proved on the similar lines. So let xn be, so we will use the sequential criteria to show that this limit exists. So let xn be any sequence in AB converging to A. So xn is any sequence in AB converging to A. So since xn is a convergent sequence, so this implies xn is a Cauchy sequence, because every convergent sequence in R is a Cauchy sequence. So this is a Cauchy sequence in AB. So this implies by, so as f is uniformly continuous on AB. So by previous theorem, that image of a Cauchy sequence under a uniformly continuous function is Cauchy sequence. So as f is uniformly, so this fxn is a Cauchy sequence in R, and we know that every Cauchy sequence is a convergent sequence. So this implies fxn is convergent in R. So let limit n tends to infinity fxn equal to L. So now we have to show that any other sequence that converges to A has to converge to this L. Then by sequential criteria of limit, we can say that limit x tends to A positive fx exists and equals L. So we will take any other sequence. So let yn be any sequence in AB converging to A, or we can say, let us call it L1 because we will use the limit of L2 also. So let us call it L1. So claim f of yn also converges to L1. So for this, what we will do, we will use the fact that since xn converges to A and yn converges to A, so this implies xn minus yn converges to 0. So this xn minus yn converges to 0. So since f is uniformly continuous, on AB and xn minus yn is a sequence, xn minus yn converges to 0, and xn and yn being two so limit n tends to infinity f of xn minus f of yn has to be equal to 0 because f is uniformly continuous on AB. So this limit should also converge to 0 by uniform continuity of f, and this implies limit n tends to infinity f of xn is equal to limit n tends to infinity f of yn. F of yn will converge because yn is a Cauchy sequence, so f xn will be a Cauchy sequence, f of yn will be a Cauchy sequence, and it will converge to L1. So this implies L1 is equal to limit n tends to infinity f of yn. So hence we have shown that every sequence xn in AB that converges to A, the corresponding sequence f of xn converges to L1. So by sequential criteria for limit, by sequential criteria for limit x tends to A positive, fx is equal to L1. So it exists and equal to L1. Similarly, we can show that limit x tends to B negative fx exists and equal to, say, L2. Now define f on AB to, so capital F, so we have to extend f, so define f on endpoints. In fact, define f from AB to R as f of x equal to fx if x belongs to AB, equal to L1 if x is equal to A, and equal to L2 if x is equal to B. Then f is an extension of f on AB and is continuous on AB. It is easy to see that it is continuous on AB. Hence, so one way we have proved that if f is uniformly continuous on the interval AB, then it can be extended to a continuous function on closed interval AB. Now we will assume the converse part. We will assume that f can be extended to a continuous function on AB, and we will show that f is uniformly continuous on the open interval AB. Conversely, assume that f can be extended to a continuous function f on AB. So by uniform continuity theorem, f is uniformly continuous on closed interval AB, and this implies f is uniformly continuous on open interval AB, but capital F is equal to small f on closed open interval AB. So this implies f is uniformly continuous on open interval AB, since f is equal to f on AB. Hence the theorem. So this completes your continuous extension theorem. So basically what we have proved is that if we need to talk about continuity of a uniform continuity of a continuous function on an open interval AB, then we just need to check its limit at the endpoints. If the limit at the endpoints exists, then we will say that the function is uniformly continuous on the open interval AB. But if the limit does not exist, then we will say that the function is not uniformly continuous on the open interval AB. For example, if we take the function sine 1 by x, then so for example, if we take the function, for example, if we take fx equal to sine 1 by x on 0 to 1, then we know that limit x tends to 0 positive sine 1 by x does not exist. So f is by continuous extension theorem. So by continuous extension theorem, we can easily conclude that f is not uniformly continuous on 0 to 1. Okay, so we can easily conclude that f is not uniformly continuous on open interval 0 to 1. And if we consider the function fx equal to x sine 1 by x on 0 to 1, so this is again continuous, f is continuous. Now limit extends to 0 positive, limit extends to 0 positive, x sine 1 by x is 0, we know this. So by also limit x tends to 1 negative, so at 1 it is uniformly continuous, so at continuous, so x sine 1 by x is sine 1. So by continuous extension theorem, we know that f is uniformly continuous on open interval 0 to 1. So f is uniformly continuous on open interval 0 to 1. In fact, you can instead of 1 you can have any real number b. You can have any real number b. So this is there. So this is all about continuous extension theorem. So we can see how easily we are able to talk about the uniform continuity of functions using continuous extension theorem. So this much is there in this video. Thank you everyone. Have a good day. Bye.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.